Hello, welcome to week 15, our final exam review week um, for the semester. This will be our last video lecture for the semester. So I hope you've enjoyed the class so far. So let's begin. Uh, Online comprehensive final exam, ground rules, final exam worth 200 points, and you only have one opportunity in the allotted time to take your final exam. I have five dates scheduled for you to log into Canvas and take your final exam. Final exam will be scheduled over 5 days, just covered that, to accommodate student schedules. The final exam will be a timed 3 hour exam. Once you start it, you'll need to finish it in the allotted time. So be prepared to allot 3 hours of your time for the final exam. Make sure you won't be interrupted, and you'll have 5 days to log in and take the final exam. Please make sure you're ready and have 3 hours in which you will not be interrupted for that final exam. Final exam dates and times. I'm gonna open it up on Monday, December the 12th at noon. I'm going to open it up on Monday, December 10th at noon. Final exam will remain open until noon on Friday, December 14th. So you have 5 days to take the final exam. Um, you I would ensure that you do take the final exam. I've had students email me Sunday night just before I'm going to close the class, telling me they still need to take the final exam, and it's sort of impossible to start to go backwards and try and open up things. Failure to take the final exam resulted in a letter grade of F in the course, so we need to make sure we take that final exam. Final exam will cover chapter lessons 1, 2, 3, 4, 5, 6, 7, and 8 from your textbook, homework sets and past quizzes, and also the PowerPoint presentations and lectures I've put on Canvas. I would recommend having your formula sheets and your textbook at your side when you are taking the final exam. I would also recommend you write any additional formulas, conversion factors on your formula sheets if you wish to include, diagram, pump theory, example problems, calculations, that's fine. I would encourage you to do so when you're taking your final exam. So just be prepared, have all these items readily available at your disposal when you're sitting down to take your final exam. Final exam questions will be similar to the quizzes, homework sets, and lecture examples, so there shouldn't be any surprises. If you've done well on the quizzes, I would just make sure that you review all the material before you sit down and take your final exam. There'll be a mixture of calculation problems, including pump curve problems. There'll be problems involving naming the classification of pumps based on pictures, which we've done on past quizzes, and I know I've put on homework sets for you to do. Have your calculator at your side for your final exam. Make sure you have your calculator readily available and you're not searching for it at the last minute. And a total of 150 questions of the final exam. Um, Similar to the past quizzes, the final exam is worth 200 points, just to reiterate that fact. A mixture of true and false questions, fill in the blank questions, theory questions, and calculation problems will be on the final exam. There will be an affinity law problem, water horsepower problem, brake horsepower problem, electrical horsepower problem, and an overall efficiency problem, pressure and flow conversion problem. So it's just a diversity of problems ranging from our lesson 1 all the way to our lesson 8 on hydraulics, pump hydraulics. Final exam will emphasize centrifugal and vertical line shaft turbine pumps. Not to say you may see a split case pump or a split case problem on that final exam, but I'm going to emphasize more centrifugal and vertical line shaft turbine pumps. Review your past quizzes, homework sets, and PowerPoint presentation, lectures. That's how I would study for the final exam. And please watch your units on your final exam. Just make sure you have the unit conversion correctly. That's why I want you to have those formula sheets I've given you from the very first day of class. Have those formula sheets readily at your side. And I cannot cover all the conversion factors on those formula sheets, but I would definitely add conversion factors that are not on the formula sheets to those formula sheets. Handwrite them in now so you can be ready for the final exam. Final exam outline. Please don't forget to take the final exam. Like I said, I've had students call me the night before I'm going to close the class ends, and requesting that I could, let them take the final exam, which is impossible because the class is over at a certain deadline. I have no authority to come back and open up the class. And then contact me via cell phone, 714-713-2491, or email me. There's my email address. If you call me, I'm going to let it go to voicemail first because I don't recognize the phone number. But if you leave me a detailed message and a phone number, I will call you back within 24 hours, if not sooner. So I just want to make sure that you understand that I'm readily available to answer questions and to help before you take the final exam. I cannot help you when you're taking the final exam, but will be available before you take the final exam to answer any questions or to assist you in any way possible. Let's do a little review. So true or false, an end suction centrifugal pump is a positive displacement pump. True or false? This is from our lesson 1 and 2. Anybody? The answer is false. So an end suction centrifugal pump is not a positive displacement pump. Not. Another question, similar to what we could find on the final exam. The force used to throw water from the vanes of an impeller in an end suction pump is called, out of these choices, we have pressure force, centrifugal force, velocity force, kinetic force. None of the answers above. Anybody? I think the answer is B, centrifugal force. So that force that uses to throw physically the water from the end of the impeller vanes on a centrifugal pump is called the centrifugal force. So similar questions will be on the final exam. These questions were taken from probably some of the quizzes that we had in the past. Question from lessons 3 and 4 from our textbook. The life expectancy of a bearing can be determined from 4 pieces of data. Please circle all the answers below that apply. We have load, speed, temperature, environmental conditions, all of the above. So the correct answer is all of the above. The life expectancy of a bearing can be determined from 4 pieces of data. And that's the load, the load that's on that bearing, axial load, radial load, thrust load. The speed is the RPM, revs per minute. We had somebody ask me that question. Revs per minute is speed. And temperature, what are we operating at? What is the temperature that that pump is heating up to? And then the environmental conditions. Is it a clean environment, a filthy environment? Is it a wet environment? All those play into the life expectancy of a bearing on a pump. From chapter 5 and 6, or lessons 5 and 6, the primary elements of a mechanical seal are blank components and the blank components. So is it the rotating gland, gland, B is stationary, lantern ring, C is rotating backplate, D is rotating stationary, and E is none of the answers above. The correct answer is rotating and stationary. So the primary elements of the mechanical seal are the rotating component and the stationary component on a mechanical seal. So typical question that could be on the final exam, per what we've studied in the past on our homework, lectures, and quizzes and textbook. From lesson 7 and 8, if a pumping problem, in a pumping problem, we are often required to find the flow rate and or velocity of a fluid in a pipe. So here's a typical flow rate problem, typical standard flow rate problem. So the equation commonly used to calculate the flow rate is called the flow rate or the continuity equation, where Q represents flow rate is equal to the velocity of fluid times the area of the pipe, and area is equal to 0.785 times the diameter of the pipe. So that 0.785 is pi divided by 3.1416. Find the flow rate in a 10-inch diameter pump's discharge pipe if the velocity is 12 feet per minute. So what are we trying to do? We're trying to find Q. So I'm trying to find Q, the flow rate. So find the flow rate in the 10-inch diameter discharge pipe. So Q is equal to V times A. We have 12 feet is the velocity. Velocity is shown here. This is the velocity times the formula for the area of a pipe, of a circular pipe, 784 times the diameter squared. And there's our diameter, the 10-inch diameter is there. We have the 10-inch diameter there. So what is the velocity? What is the flow rate? Sorry, what is the flow rate discharging from 10-inch diameter pipe? We can cancel out units. So the flow rate Q is equal to 6.54 cubic feet per second. And notice I didn't ask you for the units, so we just cranked it out in cubic feet per second. But be aware that on a quiz or on the final exam, if I say I want the flow rate to gallons per minute, you'll have to convert that. So we just assumed, since I didn't ask you, we just cranked it out in cubic feet per second. So the flow rate in a 10-inch diameter pipe with a 12 feet per second velocity is equal to 6.54 cubic feet per second. So typical exam problem, nothing, I don't think that's very beyond what you should have some understanding now at the end of the course. So just a typical problem 7, 8 from our lessons, from our typical problem from 7 and 8 in our lesson from our textbook. Find the water horsepower of a centrifugal pump with a flow rate of 200 gallons per minute and a total dynamic head of 130 feet. The density of the water is 8.34 pounds per gallon, and the specific gravity of 1 will always be 1. So if specific gravity of water is always going to be 1 for water. So we have our equation, which we could use the water horsepower is equal to the total dynamic head. The total dynamic head is given. The total dynamic head is given here. This is our TDH. Our TDH here. The gallons per minute is given in this problem statement right here. This is our Q in gallons per minute, which helps us so we don't have to make conversions. And then we have the specific, we have the density of the fluid is given here. That's our density of the fluid, which is there, goes in there. And then specific gravity of water is just 1, so it doesn't really play a factor in the equation, divided by the conversion factor in the denominator down here, our conversion factor here. Or we can use the easy equation, which I love, which has basically the total dynamic head times the flow rate in gallons per minute times specific gravity of 1 divided by the conversion factor. So I prefer to use the bottom equation to find the water horsepower, but both equations will work, and they're both listed in your textbook. But this is a lot easier to use than the one above. So we use that equation just to clean it up and not have to worry about the density of water. That 8.34 just makes another probability of error as we type in numbers in our calculator. We can make a mistake. So find the water horsepower of a centrifugal pump with a flow rate 200 gallons per minute, total diameter 130 feet, density of 8.34 pounds per gallon, and a specific gravity of 1. So we use that the second equation. So there's our second equation to find the water horsepower. We'll plug everything in the equation. The first number is the total. The first number is the total dynamic head. The total dynamic head is the TDH here. This is Q here. Our Q's there. We have our specific gravity here. And then we have the standard in the denominator of the conversion factor. So a lot easier to use that second equation. Don't have to worry about density. So we have 6.57 horsepower units. So the water horsepower, find the water horsepower of a centrifugal pump with a flow rate of 200 gallons per minute and a total dynamic head of 30 feet with a density of water of 8.34 pounds per gallon and a specific gravity of water of 1. The water horsepower is 6.57 horsepower units. So that's a theoretical value. That's an idealized value. It does not exist in the real world. This is the first value we need before we can crank out the brake horsepower. We can crank out the electrical horsepower. So we need this guy before we can move forward on our next calculations. Find the brake horsepower of a centrifugal pump with a flow rate 200 gallons and a total dynamic head of 130 feet and a specific gravity of 1. Now I'm giving you the mechanical efficiency or inefficiencies here with that 80%. So right here, So we're going to use the brake horsepower equation, which is the same equation as the water horsepower equation. The only difference is now we have the inefficiencies of the mechanical factoring in the denominator of the equation, and that's shown right here. Same equation as the water horsepower. Now we're dividing by that mechanical inefficiency. So we plug everything in the equation. The brake horsepower is equal to the total dynamic head. Basically, it's a lot easier to it's a lot easier to use the second equation. Sorry, I jumped a little bit ahead. It's a lot easier to use the second equation to find the brake horsepower because we don't have to worry about that density term as shown here in the denominator in the denominator up here. This guy. We don't have to worry about. Forgive me. We have to worry about this guy. So a lot easier to use the second equation to find the brake horsepower, and that's the one we're going to use. So we'll go again. We're going to use that second equation. We're going to plug everything in it, and there we go. We get the brake horsepower using the second equation, not the first equation. The first equation is valid, but it's a lot cumbersome. It's a lot cumbersome to use. So the brake horsepower, if we have a centrifugal pump with a flow rate of 200 gallons per minute and a total dynamic of 130 feet and a specific gravity 1 with a mechanical inefficiency of 80%, that brake horsepower is 8.20 horsepower units. So what's that telling us? It's telling us that the water horsepower was smaller than the brake horsepower. The brake horsepower is getting bigger, which is in the incorrect succession. The water horsepower should be the smallest value as we're doing our calculation to crank out the horsepowers. The brake horsepower has to be bigger than the water horsepower, so we're in the right direction. Now we're going to find the electrical horsepower centrifugal pump with a flow rate of 200 gallons per minute and a total dynamic head of 130 feet, a specific gravity of 1. We have the mechanical inefficiencies, and now we're factoring in the electrical inefficiencies to find the electrical horsepower. So once again, we could use the old that old ugly equation, but I'm not going to use that equation. I prefer us to use the more simplified equation. Same equation as before, as we found for the brake horsepower, except now we're factoring one more inefficiency, and that's the electrical horsepower inefficiency. So now we're going to find the electrical horsepower based upon the electrical inefficiency factored in from the motor. So we'll do our calculations again. We can use that equation, but that equation is cumbersome. It will work for us, but it's just more cumbersome to use. So we'll use this equation here. So this equation is, once again, the electrical horsepower. Same equation as the water horsepower. Everything's the same, except we're factoring in two inefficiencies for the electrical horsepower. We're factoring in the inefficiency for the mechanical, and we're factoring in the inefficiency for the electrical motor. So now we can crank out the electrical horsepower, and it's got to be bigger than mechanical horsepower, and yes, it is. It's 9.12 horsepower units. So we know we did our calculations in correct succession because everything's getting bigger. I'm not going to guarantee it's 100% correct because we made a little typo in when we're plugging in our numbers in our calculator, but at least we know we're going in the right direction with our calculations. Put 7 and 8, true or false. The following pump horsepower hypothetical numerical values are calculated in the following increasing order. So we just discussed in the previous slides. We just discussed that there's the water horsepower has got to be smaller than the brake horsepower. The brake horsepower has got to be bigger than the water horsepower. Then the electrical horsepower has got to be bigger than the brake horsepower. So we did our calculations. We came up with the water horsepower on the previous slides at 6.57. We came with the brake horsepower has got to be bigger than the water horsepower, 8.20 horsepower units. And then finally, the electrical horsepower finally calculated at 9.12 horsepower units. So we know we did our calculations theoretically correctly, just to hopefully to make any numerical value errors in our typing our values in our calculator. So it's true. Yeah, it's got to be true. That is correct. True or false, the vane is a portion of an impeller which throws the water towards the volute case. That is true. 7 and 8 lessons. So one of the major causes of cavitation in a pump is not meeting the available net positive suction head, not meeting the required net positive suction head, pumping muddy water, excessive heat, none of the answers above. So we talked about cavitation, which is a phenomenon which it basically tears apart our pump volute case and impellers, and also plays a part, cavitation also plays a part in destruction of valving also. So the answer is not meeting the required net positive suction head. We'll create the high probability of we're going to have a cavitation issue in our pump and our pumping system. Which net positive suction head equation below is correct for the condition of not experiencing cavitation? So what is it? Net positive suction head is got to be greater. Net positive suction head available. It's got to be greater than the positive suction head required. Net positive suction head available is less than net positive suction head required. Net positive suction head required can never equal net positive suction head required. Net positive suction head available is equal to net positive suction head required. All of the answers above. What is the correct answer? The correct answer is A. In order not to have cavitation, net positive suction head available, which the engineer calculates, has got to be greater than the net positive suction head required based upon the pump curve per the manufacturer. So the manufacturer will give us a net positive suction head required curve on the pump curve when we buy that pump. The engineer will crank out a net positive suction head available calculation, and it's got to be greater than the required net positive suction head, the one the engineer will calculate the available net positive suction head. It's got to be greater than. And I told you before that the book says equal to or greater than. We never want it to be equal to. We need to have some flexibility of factor of safety. So we like to say when we do our calculation that the net positive suction head should be a minimum for water 5 feet above the required net positive suction head per the manufacturer's recommendation, and for wastewater should be a minimum of 7 feet above the net positive suction head required per the manufacturer. So that gives us a factor of safety, so that we know we're not going to be right on that line of probability of cavitation with our pump. Last comments and updates. I'll be available to answer questions or to clarify anything that might be unclear. So I'll be available to you to help you in any way possible to prepare for your final exam or to answer any questions. I would use your study time wisely and efficiently in studying for your online final exam. I would review past quizzes and homework sets in preparation for your final exam. I would take the practice final exams as tests to see if you are ready to take your final exam. So I made a practice final exam, 50 questions from all our lesson plans. So I just pulled 50 problems from everything we've covered over the semester. I made a practice exam, final practice exam for you to utilize your time wisely, take the practice exam. You can kind of see where your weakened areas to go back and review before you sit and actually take the final exam, which is a one-time opportunity to take. I want to wish everyone the very best success on your final exam. It's been a pleasure to be your instructor for this class. I want to wish everyone a very happy Christmas and a winter break, and thank you very much.